In lesson 2.5, our two objectives are to analyze and graph rational functions. The base rational function that we are used to seeing is a butterfly graph. We may also see a variety of volcano graphs, but by and large, we're going to be looking at graphs that have the look of butterflies with vertical asymptotes and horizontal asymptotes. The second part of that will be solving rational equations, and we'll do that the second day. So we'll break it down into two parts. The first day we'll get comfortable with what the graphs of rational functions look like by exploring their end behavior, by exploring their vertical and horizontal asymptote behavior, also where they cross the x and y axis. What I'd like you to do for today in your homework is to work on page 138, work through 1 through 29, the odds. That should get you through all the graphing features of the rational functions. So there are some things I'd like to review with you, some key concepts in rational function graphs. These we covered last year into some detail, probably not as in much depth, but there are definitely some carryover of the skills that you had last year, so hopefully you retain some of that, and this will be a reminder of those ideas. First thing I'd like you to remind you to do is factor both the numerator and denominator completely. It's important to get those factors so that you can find the vertical asymptotes and also the x-intercepts. So a lot of times the first thing that you want to do is make sure you factor that numerator and denominator. The second thing you want to probably look for, are there any holes in the graph? Now, you find holes in the graph if there's any common factors in the numerator and in the denominator. If you have that, it'll look something like this. You might have an x plus 1 all over an x plus 1 times an x minus 2. If you have common factors in both the numerator and denominator, then they can reduce, which will be 1 over x minus 2. Now, this concept we reviewed earlier this year. This is called removable discontinuity. That's why I think it's so important for you to factor first, so that you can find this removable discontinuity, and also you'll see where it comes in handy for our vertical asymptotes and x-intercepts. So that's the first thing I would look for, are some holes. The second thing, vertical asymptotes. The vertical asymptotes are the zeros of the denominator. So what we're going to do is we're going to look at the denominator, and any of those that did not get reduced, so here's the one that did not get reduced, didn't have a common factor. We look at the associated zero of this factor, which means there'd be a vertical asymptote at x equals 2. Now the vertical asymptote and the holes, anytime you have holes and vertical asymptotes, you're really going to have to restrict your domain. So also in this, you're going to have domain restrictions. So see what things, associated zeros there are with the holes and the vertical asymptotes, and you'll also describe what your domain is. To find the x-intercepts of these graphs, what we want to do is we want to make sure that we set the numerator equal to 0, because that is the zeros of the numerator. So in this case, what I have in this example, there would be no x-intercepts, because there's no way that you can make this fraction equal to 0. If it's 1 over x minus 2, you want to set it equal to 0. A zero function basically says it's an x-intercept, and you know it's going to be x comma 0. So you want to force the y values to equal 0, and that's what I've done here. A lot of times we'll start off with this looking as f at x equals, our f at x is our y value, substitute in a 0 for that, and as I said, this would be impossible. What we can't do is we cannot have the denominator equal 0, so there's nothing to worry about there. The key concept is anytime you want a fraction to equal 0, the only thing that you have to worry about is what would make the numerator equal 0. So don't worry about the denominator at all. So if I were to create a different example and go x minus 2 all over x plus 1 times x minus 3, and I want to find the 0 of that function, or the x-intercepts, all I need to do is focus on the numerator, so right up here. And that would be when x is equal to a 2. If x is 2, then our fraction will equal 0, therefore it has to be an x-intercept. The one that probably takes a little bit more time and energy to think about, I'm going to clear this off, are the horizontal asymptotes. There are 3 different possibilities for horizontal asymptotes, and we've got to make sure that we go through these rules and how to find the location of them. First of all, whenever you're doing horizontal asymptotes, remember that horizontals always model the end behavior of the graph. Don't look in tight towards the origin or your vertical asymptotes. Look at what happens when x approaches infinity. So they're going to explain in the book what happens to the limit as x approaches infinity from the right side, from the left side. So they're going to think of it as a limit concept, but we're going to think about it going from a positive or negative infinity. Okay, so let's talk about the 3 different scenarios that can happen. As I explained here, it's a matter of degree. Whenever you're looking for horizontal asymptotes, you want to look at the degree of the numerator, and you're going to compare it to the degree of the denominator. And if the degree of the numerator is less than the degree of the denominator, then your vertical asymptote will always be at y equals 0. Okay, so that's pretty simple. What we would see is we'd see maybe an x minus 1 all over an x squared minus 2x plus 3. If we were to think back to what the degree is, this is a first degree polynomial. Based on the highest power is a 1. You always go to your leading term. It's very similar to your leading term test that you've been working on. This is a second degree polynomial. Anytime the degree on the denominator is bigger, or in the way that this one is worded, if the numerator is smaller, it's a first degree, and the bottom is a second degree, your horizontal asymptote will be at y equals 0. So that's an easy case if they give you an example like that. The second situation is, what if the numerator, degree of the numerator, is equal to the degree of the denominator? So now they're exactly the same, which means I would have to add another factor up here, maybe an x minus 2. When I did that, now I have a second degree polynomial over the other second degree polynomial. So in order to get your replacement of the horizontal asymptote, it'll be the ratio of the leading coefficients. In the example that I have here, if you multiply these two together, you just have an x squared. So your leading coefficient would be a 1. This x squared is a leading coefficient of 1. So you write the ratio of the leading coefficient of the numerator, which is 1, all over the leading coefficient of the denominator, which is 1. So your horizontal asymptote would be y equals 1. So what we'll do is we'll look at the degrees. If they're tied, make a ratio of their leading coefficients. And the last situation is the one that's the most fun, and that is when the degree of the numerator is 1 greater than the degree of the denominator. So this is where the numerator is going to be a larger power than the denominator, and we want it to be greater by a factor of 1. If it's greater by a factor of 1, it's called an oblique asymptote. We can have asymptotic behavior that does not follow this rule where there's just 1 greater. The numerator could be 2 greater than the bottom denominator, or it could be 3, but then they'll follow quadratic asymptotic behavior, or they'll follow a cubic asymptotic behavior. But by and large, we're always going to be much focused on the oblique asymptotes where the numerator is 1 greater than the denominator. So you'll be looking at, it could be an x cubed plus 2x plus 3 all over x squared minus 1. This is one where we would find an oblique asymptote because the degree is a third degree on the top and it's a second degree on the bottom, which means the top is 1 larger than the bottom. Now, we're going to find the location of this oblique asymptote by either performing synthetic division or long division. If, like in the case of what I have down here, if this is not a linear factor or a linear divisor, then we will be forced to use long division because there's no good way of doing synthetic division if it's not a linear factor. So that being a squared makes us go into the long division. If I would remove that and I just bring these both down 1 power, if this was an x squared plus 2x plus 3 all over an x minus 1, now it's still a matter of a second degree versus a first degree, so there's still 1 degree higher in the top than the bottom. So we're going to find an oblique asymptote. This time, since this is a linear divisor, we can use synthetic division, and we can find our location of the oblique asymptote there. So when we do this, whether it's the long division or the synthetic division, go through your whole process of doing this, disregard the remainder, and what you will find is the rest of it, whatever's left if you disregard the remainder, is the location of the oblique asymptote. So it's going to be an equation formed by the depressed equation by long division or by synthetic division. And you'll see this throughout the lesson. So now an oblique asymptote is not technically a horizontal asymptote, but I threw it under there because while you're looking for this degree of the numerator and denominator, you'll be processing, is it a horizontal at y equals 0? Is it a horizontal at y equals a ratio of leading coefficients? If it's neither of those, then maybe there's a oblique asymptote. Officially, as I said, it's not a horizontal asymptote, but when we're searching for the horizontals, it's just a good idea to try to pick up the oblique. So let's move on to our first example. As I said, these rational functions are basically a butterfly graph. Our base function that we're going to look at is y equals 1 over x. That's what most of these will have the appearance of. A rational function, by definition, is the quotient of 2 polynomial functions. So we're going to be looking at linear, quadratic, cubic, quartic, maybe fifth-degree polynomials, but one stacked over the other. And you see some concepts of limits as they're looking at describing their behavior, both at the vertical asymptotes and the horizontal asymptotes. We're going to cruise down here and we're going to start working on some examples. And in the directions, they want you to find the domain of each function and the equations of vertical or horizontal asymptotes. So I think as good practice, what I always try to do is I try to write the function in factored form. As I said, first thing I would do is try to write that. Sometimes it's more helpful than others, but I think it's still good practice to get into. So that's going to be 5x plus 1 all over x plus 5. Now there'll be times when I move back and forth between the one written in standard form and the factored form as I try to get information more easily. We're going to look at the denominator of this problem in order to help us figure out the domain. Typically, the only thing that we're ever going to have to worry about in a rational equation is is that the denominator equals 0. There shouldn't be any radicals in here where we're taking the square root of a negative number. That would be a rare occasion if I don't even think I've ever seen that. So really our domain is going to be restricted by never letting the denominator equal 0. So the domain is going to be, and I'm going to write it in set Miller notation, x is an element of real numbers, such that. Now, the only thing I can't let x be is a negative 5 because I'm going to use the associated zeros of this factor x plus 5. So x cannot equal a negative 5. Okay, so the domain is taken care of. The next thing is the location of the vertical asymptote. You'll see as we go through this lesson how the domain and the vertical asymptotes basically mirror each other. But don't forget the domain will also have to include any holes once we get to that section that pertains to holes. So we'll have a vertical asymptote at any associated 0 with the denominator. And again, our associated 0 with the denominator is x equals a negative 5. So we're kind of looking at that as a factor of x plus 5. And if the factor is x plus 5, then the associated zeros at a negative 5 for both the domain and the vertical asymptote. The location of the horizontal asymptote, that's a matter of degree. That's what I keep repeating to myself. It's a matter of degree. The numerator is a first-degree polynomial. The denominator is a first-degree polynomial. So if we want to figure out where the horizontal asymptote is, if there's a tie in the degrees of the numerator and denominator, then we're going to go with the ratio of the leading coefficients. So in the top, the leading coefficient is 15. In the bottom, the leading coefficient is 1. So we write the ratio. So keep in mind, if it's a tie, do the ratio of leading coefficients. So take the numerator, which is 15. So our horizontal asymptote is going to equal 15 over 1. Or simply, we have a horizontal line at y equals 15. So those are the three components they're asking you to find in this example. And now we can move on to the next. In the next example, h at x, like I said, as a matter of good practice, I'm going to try to factor the numerator, and it will factor into x minus 3, x plus 2. And we got to divide it by a factor of x plus 4. Okay, whether you want to put parentheses or not, doesn't make any difference. But I can look quickly now and see that there aren't any common factors to an x plus 4 in the numerator. So there will be no holes in the graph. I know it doesn't ask us for that, and later they will, so I'm just trying to get your mind wrapped around always looking for holes. The domain, in this problem, the domain is going to be any zeros associated with the denominator. The 0 that's associated with the denominator is at x equals negative 4. So x will be an element of real numbers such that x cannot equal negative 4. Then we'll look for vertical asymptotes. Vertical asymptotes mirror very closely the domain, so what we're looking at is what are the zeros of the denominator, and that is when x is equal to a negative 4. So we're always really associating vertical asymptotes with the associated zeros of the denominator. Next thing we're doing, we're going to look for the location of any horizontal asymptotes. A horizontal asymptote models the end behavior well. It's a matter of degree. So what we have is a second degree on the top and a first degree on the bottom. Okay, so by our rule, this will give us an oblique asymptote. An oblique asymptote is officially not a horizontal. So what kind of horizontal asymptote is there? There is none. So we would respond, there's no horizontal asymptote. So we would be done with this problem if that's all they're asking us. If we would not have to find the oblique. But as long as I have that here, I think I'm going to run through how to find an oblique and give you a little glimpse of what you have to do with it. The nice thing about this example is we have a linear factor on the bottom, so we can use synthetic division. So what I'm going to do is I'm going to put the associated 0 out front. That's a -4. I'm going to put in the coefficients of, and now I want to go back into this standard form of 1, -1, and -6. We're going to run through with our synthetic division, and we'll see what we have left. Remember, all we're going to do is we're going to disregard the remainder and take whatever's left. Start off with a second-degree polynomial. When we get done, we're going to depress it to a first-degree polynomial, which really means it's going to be a linear equation. So it's going to be a line that's going to tell us the end behavior of this function. So we drop down to 1. -4 times 1 is a -4. -1 and -4 is a -5. -4 times -5 is 20. 20 and a -6 is 14. Now this last step, I really don't need it because once you start figuring this out, remember, you will disregard the remainder anyway. All you'll do is you'll pick up the coefficients for your new equation, which is a first-degree polynomial, which says if we want to find the location of the oblique asymptote, it's going to be a y equals, it's going to tell us the location of the oblique asymptote, and since it's a first-degree polynomial, it'll be x minus 5. Once again, this question wasn't asking for you to find the oblique, but I thought it'd be kind of a good idea to come back and review that with you quickly so that you have an idea. This is a little bit simpler than some of the others that they give you for finding the oblique. So, bottom line, run through your synthetic division, ignore that remainder, you don't need it. Pick up the other coefficients that you have in your synthetic division, rewrite it as your reduced or depressed equation. It was second-degree polynomial to start off with. Our remaining one will be linear. Here's our linear oblique asymptote.